Now, hello everybody, and welcome to this new edition of this webinar of differential geometry in Latin America. And it's a pleasure for us to have today as our speaker to Pedro Gaspar from Universidad Católica de Chile. Is it okay? Okay, good. And he will talk today about heteroclinic solutions and a Morse-theoretic approach to an Allen-Cahn approximation of mean curvature flows. Okay, thank you, Pedro.
Thank you very much, Adrian. Thanks everyone in the organization for the kind invitation, for accommodating a date and a time for this talk. So I'm really happy to give this talk here in this webinar. Well, I have two, maybe not announcements, but maybe two things I wanted to say before starting the talk. So the first one is that the main results are all joint work with Jingwen Chen, who is a postdoc at University of Pennsylvania. And the second one is that I believe there are so many people in the audience who probably know much more than I do about Morse theory. But the idea is to present some results that we were able to get. Some of them are already published. Some of them are ready to come out of the oven. So we're going to post a preprint, hopefully very soon. But the idea is that we can use some basic ideas, some basic results from Morse theory to understand a little bit about mean curvature flows. So in particular, we would like to construct some special mean curvature flows with some interesting geometric properties using Morse-theoretic techniques for a special approximation of these geometric flows. So let me tell you a little bit about why do we care about mean curvature flows? Why is it important for us? Maybe to motivate the problem a little bit, okay? So the mean curvature flow, I think it's not incorrect to say that it's probably the most studied extrinsic geometric flow. And this is kind of easy to state. What is the mean curvature flow? So you can imagine it's a one parameter family of embedded or immersed, isometrically immersed hypersurfaces in some Riemannian manifold. So this parameter is, again, a real parameter that we usually call the time. But the idea is that this evolves according to this time in the direction of its mean curvature vector. So this means that if we fix a point in the domain, in the surface sigma, then we have a curve whose tangent vector is for every point and every time the mean curvature vector of the time t embedding of this surface. And kind of funny that this flow actually started with ideas from PDEs. So the first two names, Lichnewsky and Teman, actually introduced this flow as a parabolic version of the minimal surface equation. And then I think back in the late 70s, Kenneth Brack introduced a monumental result, a monumental set of techniques to study this flow using ideas and tools from geometric measure theory. And I think this is very impressive because this is basically during a time when some tools of geometric measure theory were still being developed. But from there on, I think the problem really became popular among geometers, among analysts. So here are some names that have some very important contributions to the study of this flow. And of course, this flow also has application in other areas. For instance, it's an interesting tool in shape optimization problems. In particular, it's used to maybe to study problems related to isoperimetric problems and also some problems in topology. But for the purpose of this talk, I want to discuss this problem from two particular perspectives. The first one is some sort of variational and dynamic perspective, and the second one is an analytic perspective. So what do I mean by variational or dynamic perspective? So if we recall from basic differential geometry courses, the first variation of the area of a hypersurface is given precisely by the negative of its mean curvature vector. So that means that we can write the evolution equation satisfied by this family of immersions as the time derivative of this family is given by minus the derivative of the area. So this means that the mean curvature flow can be regarded as a natural type of gradient flow for the area of hypersurfaces, that is, for the area functional. In particular, if you compute the variation of the area of these immersions, this equals minus the square of the norm of the mean curvature vector for all times. So this means that equilibrium points for this equation are, that is, stationary mean curvature flows, are minimal surfaces or minimal hypersurfaces more generally. And this is usually the type of geometric objects that I was interested in before starting working on this problem. But keeping in mind that relation between gradient flows and the mean curvature flow, there is a very natural question that we can pose, which is, well, we know back from Morse theory that for a nice function, that is for a Morse function defined on some space, there is a close relation between the topology of the domain of this function and the set of its critical points, which can also be seen as stationary points for the gradient flow of this function. Then we are interested in trying and implementing this strategy from Morse theory to this area functional defined on some generalized space of hypersurfaces in our manifold. But of course, this comes with some difficulties, especially from the analytic perspective. And this is because even though the mean curvature flow is a more or less natural equation to state from the geometric perspective, analytically, it's a quite complicated equation. So you could, for instance, try and write this equation for a hypersurface in the Euclidean case. So if you remind that the mean curvature vector is nothing but the Laplacian of the position vector, we would see this equation that looks, some kind of inoffensive. It looks very much like the heat flow for the isometric immersion. But then there is a catch, which is that this Laplacian is actually the spatial Laplacian, is the Laplacian along the immersion. So this means that actually this equation can become quite degenerate. And in particular, this equation is highly nonlinear. And what happens for highly nonlinear equations is that they might develop singularities in finite time. So for instance, at those points where the mean curvature blows up, you ought to see some singularities along this flow. And I think there are many classical examples. For instance, if you start the mean curvature flow with a round sphere in the Euclidean space, this is going to move in the direction of the inward pointing normal vector. And eventually, in finite time, this is going to shrink to a point. Another classical example is a cylinder in Rn that's going to shrink in finite time to its axis of symmetry. But there is a more interesting example, which is closely related to the examples that I wanted to discuss, which is this dumbbell-shaped surface. So imagine that you connect a pair of spheres with a very thin cylinder in a smooth way, in a way that you have a smooth surface, and you run the mean curvature flow with that initial condition. So along this cylinder, the idea is that if the cylinder is very thin, then the curvature is very high, meaning it's going to move towards its center, its axis of symmetry very fast. So in finite time, this is going to collapse to a neck. And at that point, the curvature blows up and we have a singularity. But it's not hard to imagine that the singularity is not too bad, in a sense that we should be able to cut out this thin neck and keep the flow going in a way that if we cut it out and keep the mean curvature flow running, we see these two disjoint spheres that once again will collapse to 2 points in finite time. But the thing that I wanted to emphasize here is that if we're able to make sense of the mean curvature flow after singularities, we maybe could detect not only what's going on with the geometry of these surfaces, but also we should be able to detect change of topology. So in particular, it would make sense to try and understand what happens when the mean curvature flow changes its topology, but also whether we can connect stationary points that might have distinct topologies using a mean curvature flow in the sense that it can be regarded as a gradient flow of the area function. So this is the basic motivation, this is the basic idea, but coming from a geometric background, we want to run away as much as possible from doing hard analysis. So in some sense, I don't want to keep track of those singularities. I don't want to get a deep information about how the curvature blows up. But instead, I want to define some generalized flow or some sort of regularization of this flow that allows us to go through singularities in a nice way, in a more analytically stable way. And for the purposes of this talk, I want to discuss a phase transitions-based approach to this geometric flow that's based on this PDE that you can see on the screen that's called the Allen-Cahn equation. So this, again, innocent-looking PDE, it's a semi-linear elliptic PDE, actually arises from mathematical models from phase transitions. It also shows up in chemistry, back from the works by van der Waals. But the idea is that this is a variational PDE that can be seen as the Euler-Lagrange equation for this functional. So this energy functional that we call the Allen-Cahn functional is basically the Dirichlet energy of a function defined on a Riemannian manifold M with a small weight that I would denote by epsilon, plus the integral of a non-linearity W composed with U with a weight of 1 over epsilon. And this linearity is very special. So we denote it by W, and I think this is very suggestive. So the classical example of such nonlinearity is this polynomial function 1 minus U squared, that if you plot this graph, you're going to see a W-shaped function, a W-shaped graph, with two absolute minima at -1 and +1, and one local maximum in between at U equals 0, which are, of course, constant solutions for this equation. But the interesting thing about this equation in connection to the area functional is that this energy can be seen as some sort of regularization for the area. So the heuristic argument is as follows. So imagine that you have for every small epsilon a function U epsilon defined on your manifold in a way that the energy is uniformly bounded. And because you're taking this weight epsilon to limit to 0, what happens is that the integral of W composed with U must remain finite. And the only way this could remain, not only finite, sorry, it must go to 0. And the only way this could happen is if almost everywhere on your manifold, U epsilon converges to plus or minus 1, which are the zeros of W. And more interestingly, in the case where your functions U epsilon are solutions to that PDE, this is going to happen in the most energy efficient way. And what do I mean by that? Is in the transition region, in the region where your function jumps from -1 to +1, which is what we call the diffuse interface, which can be regarded as the region where your functions are close to 0, you're going to see some sort of convergence. So this transition region is going to become thinner and thinner, and this is going to approximate a codimension 1 surface that turns out to be a critical point for the area. So in some sense, critical points for this energy converge to critical point for the area functional, maybe in a weak sense. Yes, I can see.
Yeah, hi. Can I just quickly ask one thing? So
yeah, sure.
I'm just trying to understand. So the Allen-Cahn equation is it typically determines the interface between two unmixable fluids, right? I'm trying to understand how the interface relates to U before the critical limit. So what is U? I mean, how I understand that at the limit, you're going to have two regions on your manifold separated by a submanifold, by a codimension 1 submanifold gamma. Is that right?
That's right. That's precisely what I mean.
Okay, but what about time 0? So what is the initial setup? How do you? What is U? Is U a density? How do you think about U?
For the moment, I'm treating U as a function defined on the manifold that is a classical solution to that PDE. So roughly, the nodal set of those solutions should be somewhat close to that minimal hypersurface.
Yeah, but what is U originally describing, right? So if you start the dynamics at time 1, what is U? right?
Yes,
What is that
it's
quantity?
that's right. It's some continuous density that somehow, it's close to -1 in one region and close to +1 in a region where you should see those immiscible fluids.
Right.
But
So
I think in the, I'm
go
sorry,
ahead, please.
I was just going to comment that I think in the work by Allen-Cahn, they were interested in a continuous model for interfaces between metals in metal alloys.
Right.
So the
So
regions
your
where
function is kind of, you have two broad regions on your manifold where the function is mostly -1 on one side, mostly +1 on the other. And there's some continuous transition happening in the middle, which is messy. And then as you take the sort of gradient flow of this energy, what it's going to try and do is separate this, right? So it's going to try and become as close as possible to a step function.
Exactly. In the limit, as epsilon goes to 0, this is exactly what you should see, right? -1 in one side, +1 in one side. But the idea is that this messy transition region also has an interesting geometric property, which is it's trying to somehow minimize this jump from the two phases in energy efficient ways. So that's because this should approximate some minimal hypersurface, right?
Right.
It's messy, but in some sense, it's geometrically not so messy. Does that make sense?
Does make sense. So W here is to be thought of as sort of a wall potential.
Exactly. It's exactly.
Got it. Okay. Thank you. Thank you.
Yeah. Thank you for the question. And not only this is going to work as some sort of regularization for the area in a way that you're seeing these bulk regions at +1 and -1, but also the gradient flow for this energy in some sense approximates the gradient flow for the area. So that means that if you have for every small epsilon a solution to the parabolic version of that PDE, as epsilon goes to 0, you should see some sort of weak mean curvature flow. And I just mentioned some names that contributed to this whole convergence theory. I think this actually dates back to works by De Giorgi in the 70s, but there are so many contributions by many people. And my idea is, I don't want to make it too technical, but I want to explain how we see this convergence from the perspective of geometric measure theory. So very roughly, we can associate to each solution to that elliptic or to the parabolic equation a measure on your manifold, which is basically taking that energy, the function that you integrate to get the energy paired with the volume form. So basically, it's the energy density associated to that energy function. And the idea is that under very reasonable uniform bounds, so for instance, if you assume that the energy is uniformly bounded, that the velocity of this parabolic motion is uniformly bounded, then you can take the limit as epsilon goes to 0 for these energy densities, and they will converge to some measure that I denote by VT on your manifold, that is some sort of weak solution for the mean curvature flow. So the idea is that VT, the limit measure, is for every time a measure whose support is concentrated on an n-1 dimensional surface that possibly has some singularities, but it's almost everywhere smooth. And at those points, you should see a mean curvature vector in a way that this object is a weak solution for the mean curvature flow. So that is, in very simple words, if you take the energy density associated to a solution to that parabolic equation, these densities concentrate on a weak solution, on a measure-theoretic solution for the mean curvature flow. And those are exactly the objects that were introduced and that were studied by Kenneth Brack. And I think a picture in many situations are worth 1,000 words. So I wanted to tell you how that convergence looks like, or what is the picture that I'm trying to visualize. So the idea is that you should see, if you plot a graph over your manifold, the graph of U, you should see these regions, these large regions where U approximates -1 and +1. And this thin interface that in some sense moves in the direction of the mean curvature vector. But there are two catches, two analytically complicated things that could happen. So the first one is, of course, this is only a weak solution. So it's very possible that the limit object could come with singularities. So it should be seen as a n-1 dimensional surface, possibly having some singular set. But there is a more annoying phenomenon that could happen, which is close to your interface, the solution could quickly jump between -1, then to +1, and then back to -1 again. So in that sense, you should see that the nodal set of the solution, the zero set of those solutions, might have two connected components that collapse as epsilon goes to 0 to two copies of your hypersurface. So this means that in some sense, the limit energy, the limit measure could happen with densities, with integer densities. So in the limit, you could see integer density mean curvature flow, integer density weak mean curvature flow. And even though that sounds complicated, these measures with integer densities are not a very close approximation to a smooth mean curvature flow. What I wanted to explain is that you could still use that convergence theory, and you could still use Morse theory for the energy functional to try and produce some interesting mean curvature flows under some situations in which you can maybe prove some regularity, and under which you maybe can make sense of the asymptotic limits in time for this weak solution to the mean curvature flow. So okay, so that's basically the idea. I want to construct eternal weak mean curvature flows, meaning weak solutions for the mean curvature flow that are defined for all times in compact manifolds using these Allen-Cahn equation. So I think this is maybe a good place to stop and to see if you have any questions, any comments before I move on. All good? Okay, so perfect. So I have a few things about how we can actually approximate a given minimal surface by solutions to the elliptic Allen-Cahn equation. But I want to skip that for a second to tell you more or less how the entire strategy looks like. So the idea is take your favorite unstable minimal surface in a compact Riemannian manifold and find a solution for the elliptic Allen-Cahn equation that converges to that minimal surface as epsilon goes to 0. So this is what we call an Allen-Cahn approximation of that surface. So if that's a stable surface, you should see an unstable manifold as an unstable manifold for the energy functional, so that we can look at all flows, all the gradient flows for the energy that converge back to that critical point as t goes to -infinity. So hopefully we can find some interesting flow that again flows back to that Allen-Cahn approximation backward in time, and that forward in time converges to some other non-constant solution for the Allen-Cahn equation. That is, to another critical point for the energy. And of course, the first question you may ask me is, well, can we actually do that? Can we actually approximate minimal surfaces by solutions to the Allen-Cahn equation? And that's exactly the thing that I skipped in the previous slide. So the answer is yes, generically, for minimal surfaces that are homologically trivial, that separate your manifold into two pieces, this is actually possible. And this result is actually due to Packard and Ritoré. We have some contributions by myself and Raissa Caju, and there is also some important information coming from the convergence theory of Chodos and Mantoulides. But the idea is if your minimal hypersurface separates your manifold into two pieces, and if that minimal surface is non-degenerate in some sense, then you are actually able to approximate it. That is, for every small parameter, for every small epsilon, there is a solution for the Allen-Cahn equation that is, there is a critical point for the energy, such that the associated measures converge to the volume measure of that hypersurface as epsilon goes to 0. And you're actually able to connect variational information between those critical points for the energy and the critical point information, that is the variational information for the minimal hypersurface. More concretely, for a sufficiently small epsilon, we are able to say that the index of that critical point of the energy, that is the number of negative eigenvalues for the Hessian at that solution, equals to the index of that minimal hypersurface. What that means is that if you take the second variation of the area, then you're going to see an elliptic operator, and the number of negative eigenvalues for that elliptic operator is exactly what we call the index. So in some sense, you have some continuity, some nice convergence for the index of the Allen-Cahn solutions and the minimal surface. And I think it's important to mention that in cases where you have symmetry, where your minimal surface, let's say, splits your manifold in two isometric pieces, these solutions can be constructed very directly. For instance, you could minimize the energy on one side among functions that vanish on your minimal surface, and maybe reflect that to the other side. And this is going to give you a genuine solution for that elliptic equation that preserves, in some sense, that inherits the symmetries from that minimal surface. And this is going to be particularly important because I wanted to consider that construction in a sphere where we work with minimal surfaces that have symmetries. But in any case, coming back to the general strategy, the idea is that once we know how to approximate a minimal surface by a critical point of that energy functional, again, I want to consider solutions that converge back in time, solutions for the gradient flow of the energy that converge backward in time to that critical point. That is, I want to talk about the unstable manifold of that energy. And I think this construction is more or less classic for parabolic equations. And for instance, there is a very interesting work by Choi and Mantulides where they construct ancient mean curvature flows, but they also construct ancient solution for a large class of equations that include the Allen-Cahn equation. But once we construct that unstable manifold, the idea is we want to use topological methods, or if you like, we want to use a shooting argument to say that there is a direction in the unstable manifold such that the associated gradient flow converges forward in time to some other solution to the Allen-Cahn equation, to other critical point. And for that, we also need to use some maximum principles for PDEs in order to make that shooting argument work. But if we're able to do that, we're, yes, Enrique?
So just so that I'm following you on the heuristics here. So you're considering, can you hear me? Yeah?
Yes.
So you're considering a minimal sigma, which is assumed to be the Allen-Cahn flow limit of some infinite time. I mean, this is the epsilon goes to 0 interface. What I mean, how does the previous intuition apply here? And so then you want to see if you further flow it, does it flow to another minimal surface? What is going on? Sorry.
That's the dream idea. But the complicated thing is that if we consider like a surface which is close to your minimal surface and let the mean curvature flow run, it might encounter some singularities, right?
Yeah.
So instead of directly running the mean curvature flow, we consider solutions to that elliptic PDE that approximate your minimal surface. But those are actually smooth and they're defined on the entire manifold. And for those solutions, you can actually make sense of solutions to the parabolic equation that converge backward in time, that is, as t goes to minus infinity, to that approximation of your given minimal surface.
Right, and if it does that, then you want to look at the positive infinite time limit and see if that'll give you another one.
Perfect, that's the idea.
Oh, that's really clever. That's interesting. Thank you.
Yeah, thank you for the question. And not only I want to see another minimal surface in the limit, but if we're hopeful, we want to reach a known minimal surface. So the idea is that I want to somehow produce a mean curvature flow that converges backward in time to that unstable manifold and forward in time to another minimal surface.
Cool, thanks.
Yeah, thank you. But of course, in order to implement that, in order to understand more about the forward limit for that gradient flow, we should be able to say something about its convergence in time. And for that purpose, we have to use some behavior for some asymptotic behavior for the solutions to the parabolic equation. And in PDEs, one strategy we could use is the Lojašević-Simon inequality. So this is basically a tool. I'm going to talk more about that in a second, but this basically ensures that if it subconverges as t goes to plus infinity to a critical point, this is actually going to converge forward in time. And once you have that convergence, all is left to do is to take the limit as epsilon goes to 0 and obtain a bracket flow, obtain a weak mean curvature flow. And hopefully, if you can control what happens after you take the limit in epsilon, so let's say you take the limit in epsilon, that's going to give you a weak solution to mean curvature flow, and then you want to study what happens forward and backward in time. So hopefully, the minimal surfaces that you're going to see are the same surfaces that you've started with. But it turns out that this is kind of subtle. In some sense, the limit in epsilon does not always commute with the limit in t, but I wanted to tell you about a situation where it actually commutes, and we can show that using some symmetries or maybe some improved convergence for these Allen-Cahn flows to the mean curvature flow. But this is more or less the strategy. We approximate a given minimal surface by a critical point for the energy. We consider its unstable manifold. We run the parabolic flow, and hopefully we produce some interesting Allen-Cahn flows whose limits are going to give us interesting mean curvature flows. So the situation that I wanted to describe, which is kind of a model situation, a model where everything goes smoothly, are the minimal surfaces in S3 in a round sphere. And the reason why that works so well is because we actually know what are the minimal surfaces of lowest area. So if you make a list of these minimal surfaces ordered by its area, the first one you're going to see are equatorial spheres, that is intersections of hyperplanes in R4 with the 3 sphere. And these are the minimal surfaces, again, with the lowest area. You know what that area is, and you know their Morse index. Their index is actually 1. So if you go up in the list, and this is actually quite tricky, the classification for the non-spherical minimal surfaces of least area actually comes from the solution of the Wilmore conjecture by Marquez and Neves. But it turns out that the next minimal surface are Clifford tori. So basically, if you regard S3 as the unit sphere in C2, and you take the product of 2 circles with the same radius in a way that they lie in S3, you're going to see a minimal surface that are called Clifford tori. So basically that surface, again, it's the second least area minimal surface, and their index have been computed by Urbano, who proved that their index is actually 5. But our result in this paper that we published this year is that you can join these lowest area minimal surfaces in S3 by a weak solution to the mean curvature flow, that is a bracket flow, that's defined for all times, so it's what we call an eternal flow, that converges as t goes to minus infinity to a Clifford torus, and as t goes to plus infinity to some equatorial sphere. So not only you can produce this interesting weak flow, but you're actually able to say something about the regularity. So it turns out that close to the tori and close to the spheres, these are genuine flows. They're actually smooth solutions to the mean curvature flows. So in some sense, all the singularity that you're going to see is happening in between these large times. In between these large times, in some sense, you're losing topology. You're going from a torus to an equator. But in some sense, you're able to control their asymptotic limits backward in time and forward in time. So in some sense, we say that these are heteroclinic solutions to the mean curvature flow. They converge back to some equilibrium solution, to some minimal surface, and forward to another minimal surface, right? So I wanted to give you some ideas about this construction, in particular, why we can actually implement that strategy in this particular context. So first of all, as I just told you, you're actually able to construct approximations of the Clifford torus in a way that they have the same symmetries, they have the same index. In particular, its unstable manifold is going to be a 5-dimensional manifold, right? It's going to be like a 5-dimensional family of solutions to the parabolic equation that converges backward in time to that Allen-Cahn approximation of the torus. So as any nice ODE or any nice parabolic PDE, if that's defined for all times, then this is actually converging forward in time to some critical point. So this is a solution to the parabolic Allen-Cahn equation that converges back to an Allen-Cahn approximation to the torus. And subsequently, forward in time, this is going to converge to another critical point. But since the energy decreases along the flow, this is going to be a critical point for the energy, whose energy is lower than the energy of the Allen-Cahn approximation of the torus. Now you can take the limit in epsilon to conclude that this new critical point is going to converge to some maybe singular minimal hypersurface whose area is going to be less than the area of the Clifford torus, right? Since the energy of those u epsilon plus infinity, the forward limit, is going to converge to the area of that minimal hypersurface. And once again, there are not a lot of minimal hypersurfaces, minimal surfaces in S3, whose area is lower than the area of the Clifford torus. Smooth minimal surfaces, there are only two, the Clifford torus and equatorial spheres. And we can rule the first option out by using some rigidity results for Allen-Cahn approximation of the torus. So it was proved by Fritz Hiesmeyer a couple years ago that if you have any solution for the Allen-Cahn equation that converges as epsilon goes to 0 to the Clifford torus, it has to come from that single approximation. So in other words, any two approximations for the torus differ by a rigid motion, they differ by an isometry in S3. So that means that if your flow actually decreases the energy, if it's not a stationary flow, that cannot have the torus as the limit as epsilon goes to 0. So great, right? It's not converging to the torus, so it should converge to an equator. But there is one annoying case that we need to rule out, which is as epsilon goes to 0, the minimal surface that you see might not be smooth. In the sphere, there is another example of a minimal surface, a non-smooth minimal hypersurface, which has area lower than 2 pi squared. So you can think of 3 semi-planes in hyperplanes in R4 that have an equal angle between them and intersect that triplane with the unit sphere. That's going to be like sort of the union of 3 half spheres in S3. In particular, their area is like 6 pi. So that's lower than 2 pi squared. But happily to us, that minimal surface cannot arise as a limit of Allen-Cahn solutions. And this is because, first of all, this minimal hypersurface is not a boundary. So you cannot obtain that minimal hypersurface as a limit of solutions where the solutions approach +1 in one side, -1 in other side, because this splits the sphere into 3 connected components, right? So in other words, 2 of these components are going to see the same sign for the Allen-Cahn approximations. The only way this could actually happen is if you see something similar to the picture that I just showed you, that the solution has the same sign in 2 sides of this surface, but it quickly jumps between -1, +1, and then back to -1. But that would force the limit minimal hypersurface to have multiplicity 2. The density of the limit measure would be 2, and in that case, the area would be too high. So that's ruled out by a topological argument using the area bounds. So no way we're going to see another minimal surface in the limit. These solutions connect an Allen-Cahn approximation of the torus to some Allen-Cahn approximation of an equatorial sphere. But up to now, we only said that these solutions for the Allen-Cahn flow only converge subsequently in time as t goes to +infinity. But since solutions that approximate an equatorial sphere are also rigid, they also differ by an isometry in S3. So this was a result that we proved previously with Raissa Caju, Marco Guaraco, and Henrik Mathisen. Well, these solutions actually have to converge forward in time, not only subsequently. And this is a phenomenon that happens quite frequently in parabolic PDEs. If you have some integrability, if you have some rigidity for the subsequential forward limit, this actually converges in time. And the proof of this result is based in a Loyasevich-Simon inequality, in that case for the energy functional. So basically the difference between the energy of the along the flow and the energy of the forward limit is going to be bounded up from above by the square norm of the gradient, that is, by the square norm of the derivative of the energy. And it's a known fact in ODEs and also parabolic PDEs that once you have inequality of this type, the subsequential limit is actually sufficient to tell you that this actually converges forward in time. So that is a genuine solution to the parabolic equation, converging backward in time to something that approximates a torus and forward to something that approximates a sphere. And now, as I just told you, we want to take the limit in epsilon, and that's going to give you a brachiflow, a weak mean curvature flow in the sphere that connects some torus to some sphere. But it would be great if we're able to show that these are actually the same limits that you would see if you first take the limit in time and then take the limit in epsilon, right? That they converge to the right minimal surfaces backward and forward in time. And in the case of the sphere, we can actually implement that using the symmetries of the torus and the sphere. So the idea is that any solution that converges backward in time to an Allen-Cahn approximation of the torus shares some symmetries with the torus. They don't necessarily have the SO2 symmetry, but they have some common reflections with the torus. And then looking at all Clifford tori in the sphere that are preserved by those reflections, and looking at all equators that are also preserved by that reflections, we're able to say that there is no way around, that they should connect the right Clifford torus, so backward in time they converge to the same torus that we've started with, and forward in time to the same Allen-Cahn limit of u epsilon plus infinity. So that is, we can actually construct a flow joining the right minimal surfaces. So, I think this result is kind of nice. There aren't many existence results for flows that are defined for all times in compact manifolds, even though they are singular. But this is not, the whole picture. We're only able to produce a certain family of flows. So since we're looking to the symmetries of the Clifford torus, in the previous paper with Jingwen Chen, we were able to construct a two-parameter flows that connect the right solutions, that connect the right minimal surfaces. And this two-parameter family has to do exactly with the symmetries of the torus. But it would be amazing if we're able to say, for instance, that we can connect a given torus with any equator in the sphere, right? That in some sense, if you look at all flows that converge back to that torus, if you flow that forward in time, you can reach any sphere in that way. And this is the result that we're working in, that we're basically finished. Again, hopefully this is going to appear in archive sometime soon. But in order to construct these Allen-Cahn flows, joining a fixed torus or an Allen-Cahn approximation of the torus to every Allen-Cahn approximation of an equator, the idea is that we can use some Morse theory. So here I have maybe one of the most famous results in Morse theory, one of the first results that we learn when we take a differential topology class that deals with Morse theory, that if you have a nice function, a Morse function defined on, let's say, a compact manifold, on a smooth manifold, you can actually understand, you can actually study how the topology of sub-levels for your function changes, how they change once you pass through critical level. So more precisely, if C is a critical level for your Morse function, then the lower sublevel, once you attach a cell for each critical point, whose dimension is given by precisely the Morse index of those critical points, that is, if you attach the unstable manifold of each critical point, then for homotopy purposes, you're actually reconstructing the higher sublevel. That is the level that you get after you pass that critical level. So there is a close relation between lower sublevel, higher sublevel, and the unstable manifolds in the Morse index then of the critical points at that critical level. And that's amazing because we know what are the lowest critical levels for the energy functional. So the levels that have energy strictly less than an Allen-Cahn approximation of the torus are either constant plus and minus 1 functions. So those are actually zeros for the energy, and they are the only global minimizers. And the next one in the list are exactly the Allen-Cahn approximation of equators. The only problem here is that, well, that function is invariant under symmetries, so this is not exactly a Morse function, right? Critical points are actually degenerate, and at least for those critical points, the degeneracies come from isometries. So, you know, it's not a Morse function, but it's not too far from it, right? And this is exactly what we were able to exploit. So using that description of the lower sublevels for the energy, we are able to say that for every small parameter epsilon, we are able to produce solutions to the parabolic Allen-Cahn equation that converge backward in time to something that approximates a Clifford torus, to a solution to the Allen-Cahn equation that converges to the torus, and forward in time to any given approximation of an equator. That is, again, if you take that Allen-Cahn approximation of the torus and you look at its unstable manifold and you run the flow, the gradient flow for the energy for every such function in the unstable manifold, you can reach any Allen-Cahn approximation of the equator. That in some sense, this unstable manifold connects to that set of Allen-Cahn approximation for spheres. And in the remaining time, I want to give you, just to make sure, how much time do I have?
You have some 10 minutes.
10 minutes, perfect.
Yep.
I want to give you basically, so thank you. I just want to give you maybe some key ideas that we use in this construction, that the ones specifically that are related to Morse theory. And maybe I can mention some, you know, some interesting problems related to that, some forward directions that we still think we can push that construction. And I think maybe one of the main ingredients in that construction is that both Allen-Cahn approximations of equatorial spheres and Allen-Cahn approximations of torus, they have some sort of variational characterization. So more concretely, these critical points for the energy can be obtained through a min-max procedure. So basically the idea is, let's look for every positive integer p at families of functions that lie in some Sobolev space where this energy function is defined, that have non-trivial cohomology in degree p. So more precisely, I want to look at subsets of the Sobolev space W12 that are symmetric, that are invariant under the antipodal action, and such that the quotient by that antipodal action detects the pth degree cohomology. So if we look at the family of all such sets, and we maximize the energy over each given set, and minimize the energy over all given sets, that is, if we consider the min-max number associated to that family, then we're going to see a critical point for the energy. So the classic variational theory for maybe semilinear PDEs tell you that you can actually construct solutions to the Allen-Cahn equation whose energy is given precisely by that min-max number. And precisely in that earlier work with Caju, Baracco, and Mathisen, and also in that work that I just told you about by Hiesmeyer, we actually characterized what are the lowest min-max number. So if you do that for p equals 1, 2, 3, and 4, you're going to see the critical level where Allen-Cahn approximations of equators lie. So that is, in some sense, the first 4 Allen-Cahn widths, the first 4 Allen-Cahn min-max numbers correspond to Allen-Cahn approximations of equatorial spheres. And that's kind of natural from the index perspective, because a solution at the pth min-max level should have Morse index at most p. And the fifth one, using the same analogy with the index of minimal surfaces and the index of those critical points, are going to be exactly Allen-Cahn approximations of Clifford torus, which are also minimal surfaces of index 5. So in some sense, that can be described as an Allen-Cahn counterpart of the classification of low area minimal surfaces. that those Allen-Cahn approximations of the lowest area minimal surfaces can be obtained by a min-max procedure. So that's great. We're able to characterize, we're able to describe geometrically what are the lowest critical numbers, the lowest critical values for the energy. And those are actually compact manifolds lying inside the Sobolev space of functions on the 3-sphere. So very naturally, we should be able to perturb the energy functional through Morse functions for which we can actually use Morse theory. And I wanted to tell you very quickly how we do that, maybe with a picture. Again, I think that's maybe better than tell you what exactly are the perturbations. But in the case where your ambient space is a finite dimensional manifold, for instance, 2D torus, you might see some critical manifolds in that case, the top circle and the bottom circle. In our case, that would correspond to the space of Allen-Cahn approximation of tori and Allen-Cahn approximations of equatorial spheres. And again, this is not a Morse function. If you consider the height in that torus, this is not a Morse function, but that's not too far from it. And what do I mean by that's not too far from it? That maybe if you tilt a little bit the top circle, and maybe if you tilt a little bit the bottom circle, then you're actually going to see a Morse function. So along the top circle, you're going to have now 2 critical points. And the idea is that the index of the lowest one is not going to change. Similarly, along the bottom circle, the index of the highest energy critical point is going to correspond to the index of the critical points that we had before taking those perturbations. And the construction of these perturbations is actually comes from a finite dimensional argument that was described in this work by Baniaga and Hurtubise, where they construct Morse perturbations for Morse-bot functions. So maybe implementing that idea in the infinite dimensional context of the energy functional, we're able to use that information about the topology of the sublevels for the energy. So basically we're able to describe what is the cohomology of lower levels for the energy, and we're able to maybe arrive at a contradiction argument. So the idea is roughly as follows: for a Morse perturbation of the energy, if the unstable manifold of the solutions that approximate the Clifford torus doesn't hit every sphere, or maybe if it doesn't hit the top sphere as t goes to plus infinity, if we're not able to produce the flow that we're trying to construct, then we're able to construct maybe a set in that family that we use to describe the min-max number that violates the definition of the min-max number. In other words, if we're not able to construct that flow, we're able to construct a 5-dimensional family of functions defined in the sphere whose energy is strictly less than the 5th min-max number, and in a way that this 5-dimensional family actually detects the 5th cohomology group. That is, it has non-trivial 5th cohomology group. And that's a contradiction with the way that we define that min-max number. Okay, just to conclude, I wanted to tell you that there are some, of course, analytic complications. So the first one is that the perturbations of the Allen-Cahn equations are not as nice as we would like. If you look at the gradient flows for those Morse perturbations, they are not so nice from the PDE perspective. So they actually define quasi-linear ODEs in the Sobolev space that can be regarded as non-linear PDEs. So they are not local standard parabolic equations. And well, this is not too bad because there is an existence theory for those abstract PDEs. But I just wanted to mention that the global existence, that is the fact that these solutions are defined for all times, is a bit more subtle when we compare it to the global existence for solutions to the parabolic counterpart. That is, in simpler words, there is some PDE stuff that we have to deal with to construct flows, gradient flows for this Morse perturbation that are defined for all times. And there is another analytic thing that we have to deal with, which is we need to make sure that as we take the perturbation parameter to 0, as we recover the energy function from those Morse perturbations, we need to make sure that these orbits for the gradient flow still connect the critical points that we've started with. That is, we need to understand the dynamics of the gradient flow for those perturbed Morse functions near the critical manifolds. And in some sense, that's not too complicated because the dynamics, in some sense, splits near those critical manifolds. In some sense, since we are near critical manifolds, the gradient of the energy is too small. The gradient of the E epsilon is too small. So the dynamics are dominated by the perturbation. And this kind of prevents the limit of the orbits to break when we take the perturbation parameter, when we limit that to 0. In simpler words, the limit of flows for the perturbed Morse function actually connect the critical points that we've started with. So, okay, so I think I'm basically out of time, so I just want to quickly mention two interesting problems. The first one is that this construction does not tell us anything about the singularities of the flow. And I think from the geometric perspective, that's very natural. We don't even know the answer to very basic questions, such that how many singular times do we have, or what is the geometry of the singular sets, and where are the points where the curvature blows up. But I wanted to point out something about this result that we're about to share with everyone. That is, up to now, we're not able to produce the corresponding mean curvature flow. So it seems that it's technically complicated to take the limit as epsilon goes to 0 and still obtain mean curvature flows that join the right minimal surface. But this is a kind of a work in progress, but we are cautiously optimistic that this seems to be an analytic technicality. But once we are able to maybe study the convergence of these flows backward and forward in time in a uniform manner, we should actually be able to produce the right mean curvature flows. And the issue here is that the convergence between Allen-Cahn flows and mean curvature flows it's kind of weak. It's just a measure theoretic convergence. But in any case, I hope that I could give you some impression of why using Allen-Cahn equation and why use phase transitions might be a good strategy to study mean curvature flows. So that's basically all I wanted to tell you. So thank you very much for your attention. And I'll be very happy to answer any question, any comments you might have.
Okay, thank you very much, Pedro, for this very nice talk. Okay, then now we have a few minutes for questions or comments for Pedro. Who wants to begin? Enrique.
Yeah, so maybe I can give this, maybe I can give it a shot. I mean, I'm not over the specific business of how you then go about and study mean curvature flow, but I'm always curious about this Allen-Cahn problem, because in the end, the minimal surface you recover, let's say, which for you is some sort of medium time solution, right? But this is supposed to be this minimal interface between two regions on your manifold, and then for that you need coordination 1. But another way of thinking of minimal submanifolds is as a very particular type of calibrated submanifolds, right? And in which the volume form you're using in some sense is sort of volume itself, is the Riemannian volume itself. But you could think of this broader family of problems, which is when you calibrate it by some differential form, some closed differential form on your manifold. And I always wondered, can we formulate Allen-Cahn type problem that would detect surfaces or submanifolds which are calibrated by something more general than just the volume? By did you ever give this some thought? Even in low dimensions, right? Maybe having a complex curve which is calibrated, is holomorphic, Right? Do you know of any progress in this direction?
Oh, I think that's a great question. I think that would be an amazing, maybe type of result to look for. I haven't looked too much over calibrated surfaces or calibrated submanifolds. And maybe from a perspective of someone who basically just works with codimension one objects, my impression is that there are, of course, some analytic difficulties that are, arise from considering higher codimension objects. But I think this would be a very natural strategy, right? To maybe try and approximate that by some elliptic PDE that recovers that behavior when you take some sort of limit. And maybe that's, one thing that I could mention that's not directly related to calibrations, but which is related to higher codimensions submanifolds, is there have been some recent developments in understanding functionals, for instance, such as the Ginzburg-Landau functional, or also I think it's the abelian-Higgs functional, that are some sense codimension 2 counterparts of the Allen-Cahn functional. For instance, there is very interesting work done by Daniel Stern and Alessandro Pigacci that basically construct Allen-Cahn approximations for codimension 2 submanifolds. And I think there is a preprint from this year where they actually produce like solutions for the parabolic equation, and they prove that these solutions converge to codimension 2 mean curvature flows in some sense.
Yeah, that's actually where I would be going. I mean, if I set out to try and answer this question, that's what probably I'd try and do, to try and look at I don't know if codimension 2, but for a complex version of the problem, right? So
right.
You're still in codimension 1, but you're just in complex codimension 1, and then the sort of minimal guys you would expect to find would be holomorphic curves, which indeed are minimal in both senses, right? Because the symplectic form in that case is calibration that would give you the area on a holomorphic curve, right? So you think these guys have been thinking about this?
Oh, not that I know of very much, but I think that this is a very natural suggestion. I think it's a great suggestion, especially because, at least, I don't know, we might be biased, but we believe that this construction seems very general, right? It only uses like topological arguments. I think the worst part is that we need some sort of rigidity or some generic conditions to detect those limits. But
sure, you're going to have to assume a lot of stuff, but yeah.
Yes, absolutely.
And Luis was kind enough to find us the preprints you mentioned. So
thank you very much, Luis.
Yeah, I'm going to have a look. Nice one, Luis. Okay, thank you, Pedro. Next time we see each other, I'll maybe ask a more precise question. But this was very interesting. Thanks.
No, thanks a lot. Thanks a lot for the question.
Cheers.
Cheers.
Okay, are there any other questions or comments for Pedro? Well, if this is not the case, let us thank Pedro again for this very nice talk.